I'd like us now to consider a titration that is more complicated, but is very important in terms of interpreting what goes on in a titration. This titration is about a weak acid with a strong base. The weak acid in question is methanoic acid, and it's shown right here. The strong base is once again the hydroxide ion. Key question number 4 asks us to write a balanced equation for this titration reaction and to omit any spectator ions. We do have the sodium ions from sodium hydroxide as spectator ions, so we will omit them. But is it okay to simply write the hydronium ion to represent the acid? And the answer is no. This is because we are dealing with a weak acid that only ionizes partially. The main species present for a weak acid, besides water, is the weak acid, in this case methanoic acid. Just to make the connection, methanoic acid is the simplest of the carboxylic acids and can be drawn to show the carboxylic acid functional group. A balanced equation for the titration would therefore involve methanoic acid plus hydroxide ion going to form water and the conjugate base, methanoate. Note that like all titration reactions, this reaction goes to completion, even though it involves a weak acid. This is because the reaction involves a strong base. It is worth mentioning, however, that there is a second reaction that is always occurring in the background at all stages of the titration. That is, the reaction of the weak acid, methanoic acid, reacting with water. Now this is an equilibrium reaction which does not go to completion and is described by the equilibrium constant Ka. We'll say more about this in class. Key question number 5 asks us to label our titration graph concerning the major species in solution in the Erlenmeyer before the titration, halfway through the titration, and at the equivalence point. The balanced equation can guide us with this. Before the titration, we simply have predominantly the weak acid, methanoic acid, in solution. The estimation of the equivalence point, just like with a strong acid, strong base, is represented by looking halfway along the drastic change in pH. This corresponds to a volume of 25 mils of titrant, that is our hydroxide ion, and a pH of approximately 8.2. Turning back to the balanced equation for the titration and looking at the product side, we see that the predominant species is the conjugate base of methanoic acid. This is methanoate. This is a weak base, so hopefully it makes sense to you that the pH will not equal 7, because we have more than just spectator ions present, but rather would be greater than 7 at 25 degrees Celsius. The other predominant species would be the spectator ions, the sodium ions, from our sodium hydroxide titrant. The other point in this graph that we need to consider is halfway through the titration. Given that the equivalence point volume is estimated to be 25.0 mils, then halfway to this equivalence point would correspond to a volume of 12.5 mils. At this point in the titration, half of the original methanoic acid has reacted and has been converted to methanoate. This would mean at this point, the concentrations of methanoic acid and methanoate would be equal. This is a very important thing to realize. Recall that if there are substantial amounts of both weak acid and its conjugate base present, we can use the Henderson-Hasselbalch equation to calculate the pH. Further, if the concentrations of weak acid and conjugate base are equal, as they are in this case, The Henderson-Hasselbalch equation simplifies to pH is equal to pKa of our weak acid. As we shall see, a measurement of pH at this point in the titration allows us to estimate the pKa, which in turn allows us to estimate the Ka for our weak acid. Let us now complete the key question number 6, which asks us to calculate the concentration of the methanoic acid. This is essentially an identical calculation that we did to find the concentration of our strong acid, HCl, in the previous video. I start with our balanced equation. Now consider what we know about the hydroxide ion solution. We know that its concentration is equal to 0.100 molar. And from the titration graph, we have estimated the volume of titrant at the equivalence point to be 25.0 mils, or 0.0250 liters. Now consider what we know about the methanoic acid solution. Given is the original volume of the methanoic acid solution, and this is equal to 20.0 mils, or 0.0200 liters. What we don't know, but can now calculate, is the original concentration of methanoic acid before the titration. The calculation would look like this: 0.100 molar hydroxide ions times the volume at the equivalence point, 0.0250 liters, will give us the moles of hydroxide ions used in the titration. This is multiplied by 1 mole of methanoic acid divided by 1 mole of hydroxide ions, given that they react in a 1-to-1 ratio, which gives us the moles of methanoic acid. Finally, this is divided by the volume of the methanoic acid solution, that is 0.0200 liters, to give us the original concentration of the methanoic acid. The result of this calculation is equal to 0.125 molar. Note again, this is an identical calculation that we did for the strong acid. Titration reactions involving strong or weak acids with strong bases both go to completion, and therefore the stoichiometric approach for either one of those situations is the same. Hopefully these two videos have helped you become familiar with the concepts related to acid-base titrations, which involve using a pH meter to monitor the progress of the titration. In class, we will review the calculation of how to determine the Ka from the halfway point of a weak acid strong base titration. We will also examine the other important type of titration, which is weak base with a strong acid.